A lot of things to cover. We don't have a lot of time. All right, so here's what I would like to do. I'm going to give you two formulas today. We're going to be covering chapter 21, which is a two-sample T independent test. Okay? Now, before we do that, we're only covering, so there are two types of two-sample T's. There's the independent and there's the dependent. We are only going to learn the independent, but there are questions that ask you if these are dependent, okay? So let's talk about independence and dependence, okay? The best examples of dependence, okay, it's the same person measured twice, or it could be a couple, like a married couple. That would be an example. So a husband and wife, they're married, they're an automatic couple, or the idea is you're having some sort of a matched pair. Okay? So I don't remember if I told you in this class, there was an interesting study done in Somerville, study done in Somerville, Massachusetts. They wanted to determine if they were trying to help juvenile delinquents, and they thought that having a mentor would help. So one group of kids, they gave them a mentor, and the other group of kids, they didn't, and they wanted to see if they went back to jail after. So what they did is they took two 15-year-old kids, two 15-year-old boys, let's say, and they said, okay, you get a mentor, you don't. They both come from the same socioeconomic background. So they matched them. They weren't exactly a married couple, but it was like a married couple in that they matched them. They had the same age, they were the same socioeconomic background, the same race, that sort of a thing. Okay, so that would be an example of a matched pair. Now the interesting thing about the study, the people who got mentors were more likely to go to jail than the people who didn't.
What?
Isn't that weird? So sometimes your good ideas aren't so good. Really interesting study, you should hear it. It's on Freakonomics. Or maybe it's on Hidden Brain, I can't remember, one of those two. But anyway, it's really interesting. We are not going to cover dependent two-sample tests. Okay? However, you are going to need to distinguish whether they are dependent or independent. So you can think of these as two groups with no tie to each other. So here's an interesting thing. So for example, they could be like men and women. Okay? If you're just comparing men and women, those would generally be independent. But if you're comparing husbands versus wives, that would be a dependent. Okay? Because you've matched them together. Whereas if you're just taking men separately and women separately, those would be independent. Does that make sense? Okay? So the first four problems are going to be, are these independent or dependent? Are they one sample or two sample? Okay? So let me give you a couple of examples here, and I want you to tell me if these are independent or dependent. Okay? All right, so a researcher wants to determine the effectiveness of a new medication to treat the common cold. Okay, you've probably heard of these types of studies before. They randomly divide 430 subjects into two groups. Group 1 gets the medication. Group 2 gets the placebo to see if there is a difference, see if the drug makes a difference. Okay? So are those two groups, are those independent or dependent? We're going to vote. Okay? One group gets the placebo, one group gets the medicine. Who says those are independent? 1, 2, 3, 4, 5, 6. Who says they are dependent? 1. Okay. Okay, those are independents. The majority got that right. Why did you think it was dependent?
Because I didn't listen to the question.
You didn't understand the question. All right. Let me do another one. Okay, we're going to pretend this is a stick. Okay, we're doing an experiment, and we want to see how fast it takes for a person to catch a stick with their dominant hand versus their non-dominant hand. Okay, we're going to do this with 12 people. So we're measuring how long it takes them to catch the stick. Okay.
How many tries? Just one on each
Well,
side?
it's not a pen. It's a big meter stick. So you'll catch it at 3 inches or 6 inches or whatever. Okay. So you have a chance to catch it, theoretically. So the question is comparing the dominant hand versus the non-dominant hand. Okay. Who says that's independent? You 1, 2. Who says that's dependent? You voted twice. One of those answers was correct.
Yeah, exactly.
Okay, Bettina, you said it was dependent. Why?
Well, because both arms are attached to a body, like it's one person. Like you can't do dominant separate from undominant.
The same person measured twice, right? So that's exactly right. That would be a case of a dependent. Now, here's one of my favorites. Okay? And students always get it wrong. So think hard on this one. Okay?
It's probably so simple we think it's
You
hard.
want to do an experiment to find out if there really is more stuff in double stuff Oreos versus regular Oreos. So you buy a package of regular Oreos, you buy a package of double stuff Oreos, you measure the stuff in the middle, the white stuff, okay? Who thinks that is an independent test?
Oh my gosh, I hate this question.
1, 2, 3, 4, 5. Who thinks it's a dependent test?
I'm still trying to analyze this.
1, 2. Who didn't raise your hand? 3, 4. Okay, Jordan, why do you think it's dependent?
Oh, you're saying who didn't raise their hand, so that's why
that's why
I'm still analyzing which way to go.
Okay, who says it was independent? Why, Alex? They're two different groups. Who says it's dependent?
What is this thing?
Why, Aaron?
Because the same person is testing both of them.
Because the same person is testing both of them. Okay, you're focusing on the wrong thing.
Well, you can match.
Well, it's about the
Where
same
what
brand.
is it in the
Okay?
stuff?
So,
And
okay.
some students say, well, I'm going to take cookie 1 from the regular Oreos, and I'm going to take cookie 1 from the double stuffed Oreos. But let me ask you a question. Number 1, are there even the same number of Oreos in double stuff versus regular?
No.
Okay? So the matching 1 to 1 is kind of arbitrary, right? It's just how they happen to go in the package. Okay? So
So did
Bettina,
you say it's dependent?
Bettina was right, it's independent.
Oh, good.
Okay? Those are independent. Okay?
So they don't depend on each other.
They don't depend on each other.
Okay.
You could
can't match
arbitrarily
the
say
pair.
cookie 1 and cookie 1, but it's not like they're a married couple, right?
Yeah.
They didn't come out of the factory, the double stuff's the man and the single stuff is the woman, right?
You know,
It's not like that.
it's just right.
So is
Okay.
what Alex said, like, what did you say, Alex?
What?
Your recipe.
There are two different groups that come out in separate packages. Like
Yeah.
they're not connected to each other.
They're not connected to each other, okay? So in order to be a matched pair, you have to do that. Now, except for identifying independence for dependence, independence for dependence, we are not going to actually do the math behind a dependent test. We're only going to do independence. So if you get a problem that says dependence, we can't do that. Come to my Math 2040 class, except for I'm teaching it this fall. Go to a Math 2040 class, we'll teach you how to do both of these. But we are going to concentrate only on the independence test. So, because we're short on time, I want to give you the 2 formulas, okay? Here's the hypothesis test formula. This is for independent 2 sample T, and here is the confidence interval, okay? The formula is, for the hypothesis test, T equals x1 bar minus x2 bar divided by the square root of S1 squared over N1 plus S2 squared over N2. Okay, now didn't I tell you, what is S1 squared?
Oh, you told us something about that. S squared?
S or S squared, S1 squared.
Is the sample
Is it-
variation.
It's the variance. Remember I told you that one day we'd be using the variance? We're actually using the variance in both of these. Okay? We're using S1 variance, S2 variance. Okay? And then we're square rooting it. The confidence interval formula is going to be X bar, X1 bar minus X2 bar plus or minus T sub alpha over 2 times the square root of S1 squared over N1 plus S2 squared over N2. Okay? Now, in both cases, okay, so by the way, you don't need the same N for each sample, but they should be, I don't want to say, I'm going to say close. I'm going to keep that as kind of vague. Okay? So you might have, say, 1,500 here, you might have 2,100 here, or vice versa. We'll call that close enough. Okay, or 15. You don't, but you don't want to do 3 and you don't want to do 1,000. That would be bad. Okay? So I'm not going to really define close. Most of the problems here are going to be close enough, so we don't have to worry.
So we're not gonna do this for any Z tests, only for T
This
tests?
is only a t-test.
There's no Z test formula that would.
There's no z-test for 2 samples. Okay? So let's go ahead and we're going to do an example here. Okay, I'm going to pull up a spreadsheet that I hope I can find really quickly because I don't want to type this in. I hope this is the right one. Okay, it is. Okay. And let me, here, I'll give you a little background. On Space Lab, 14 rats were sent to space. Upon return, red blood cell counts were determined. 14 rats stayed on Earth. We want to see if there is a difference in red blood cell counts. Okay? All right, so we're going to go through our normal routine. Step number 1 is
List all your important numbers.
list the numbers. Okay, 14 rats were sent into space. So I'm going to say N1 equals 14, N2 equals 14. Guess there's not much here, right? My alpha is 0.05 because it didn't tell you. Therefore, my confidence is 0.95. Oh, I forgot to mention one other thing, but we'll get to there in a minute. What else do you think you need to know? X bar or X1 bar? Yeah, we need to know X1 bar or X1, here I'll call X1 bar and X2 bar. How do I find those? Average. Okay, So we're calling one is space and x2 bar. Whoops. Okay. What else do you think we ought to know? S1 and S2. Okay, S1 is SCDEV dot S, or just plain old is fine. And standard deviation of the Earth. Okay, now really quickly, 7.8 and 8.43. What do you think? Do those look different enough to you?
Hope so.
Kind of hard to tell. We've got a standard deviation of 1. So these are within 1 standard deviation of each other. Is this like 6 heads versus 5 heads? Or do you think those are different? Just guess. What do you think?
I'm gonna go on a limb and say I think they're different enough.
What do you think of your sample sizes?
Too small.
These are actually too small, right? Okay. So they come from known distribution. I always think that's a fire alarm. Okay? Okay, so we're going to say they come from a known normal distribution, although we don't know that. But anyway, so we're going to get away with the small stuff. Okay? Anything else we should know?
No.
There's one more thing we should know. And I'll write this on the board really quick. Your degrees of freedom equals the smaller of n1 minus 1 or n2 minus 1. Now, in our case, they're the same. But if they were different, you'd use the smaller of those. Okay? So the degrees of freedom in this case is what? Is 13. Okay? If they were different, you'd use the smaller and just subtract 1. Okay? All right. Step number 2 is quantitative or qualitative. These are quantitative. Okay. Step number 3. Null. Okay. So this is a little bit tricky, but I'm going to ask Bettina and see if you can figure this out.
So our question
Is there a difference between the Earth rats and the space rats? What'd you say? Yeah.
So that's a question. So our null hypothesis is that, I mean, this is so x bar 1 is equal to x bar 2. Would that be the null hypothesis?
Who agrees with her? 1, 2, 3, 4, 5, 6. Who disagrees with her? It was a really good guess, and she's on the right track, but there's one problem with it. What does x1 bar represent?
Oh gosh.
Earth or space?
What'd you say?
Is it in space?
X1 bar does represent space. That's true, but that's not what I was going
Well, I
for.
understand that these are both x bars, like it's a sample standard
It's a
deviation.
sample, right?
But I don't know where in, like, there's no population listed.
But what represents the population?
The Earth?
Rats equal to rats.
The rats on the Earth? And it's on a normal distribution?
Mu equal 14.
You won.
You use X bar, but you were supposed to use mu, because X bar represents a sample. Mu always represents the population. So you were totally on the right track. You just wrote the wrong letter. Okay.
So mu1 equals mu2.
So now in the past, we always said it equaled a certain number. We don't know what the population is. We don't know what
Okay.
rats are supposed to be. Maybe we know on Earth, but we certainly don't know what they are in space. Okay? So you were on the right track, but you used X bar rather than mu. That was the only thing you did wrong. Okay? Now, what should the alternative be based on what is written? It's going to be not equal. Okay? Now, some of you are going to look at that and you're going to say, well, look, X1 bar is less than X2 bar. But you had to figure that out. They did not assume that space rats were going to have higher or lower red blood cell counts than Earth rats, right? So this is a one or a two-tailed test. Two-tailed test, okay? All right, step number 4. Find the test statistic. Okay, I'm going to do this both ways. We're going to do it with the hypothesis test, and we're going to do it with the confidence interval as well.
I keep thinking that it's categorical imperative because my philosophy class, categorical imperative.
We're not philosophers in here.
We kept doing CI, so I keep thinking categorical imperative.
Confidence interval. Okay. All right. Which one do you want to do first, Jordan? You want to do the hypothesis? So T equals. What's the formula?
X bar
X1 bar
minus X bar 2
X2 bar
over the square root of your S1.
S1 squared over N1 plus S2
Squared
squared over N2. Okay? Okay, can you help me punch it through?
Yeah, you're 7.8
7.88
minus
minus
the one underneath.
8.43 equals the square root of
Your S1, which is 1.017.
1.01 squared divided by 14 plus
This S2
S2 squared divided by
over 14.
the other 14. Okay, then I'll underline that, and this is going to be the numerator divided by the denominator, which is negative 1.43. Yes.
Is that the T equals whatever the same as that confidence interval over there?
No, it's this one here.
That's.
We're doing the hypothesis test.
We're doing the
Yeah.
hypothesis test.
Yes, yes.
Okay? So Alex, do you want to do the confidence interval while we're at it?
Sure.
We'll do the lower and the upper. Okay, in order to do the confidence interval, I need to add one more thing here. I need to find my t, so the alpha over 2, right? So I got 13 degrees of freedom. My alpha is 0.05, right? So which column am I looking in over here? 0.025. Remember, because it's two-tailed. Okay? And 13 degrees of freedom, so I'm on this line. The value is 2.160. Okay? 2.160. Okay? All right, so this is going to be T. No, it's going to be X1 bar minus X2 bar plus or minus T, I'm just going to call it T times the square root of blah, blah. Okay, I don't want to write all that. Okay, equals what? And you probably should use parentheses on this if you want to get it right. Okay, 7.88.
You could just take the
A
other
little
one.
lower, so it's minus 8.43
Okay,
minus
minus
0.16
2.16 times
square root.
square root.
Let's see, so we need another parentheses.
I got it in there.
Do you have it in there?
Yeah, this is good. Yeah,
We'll want another one so we can divide.
no, you'll be okay. S1 squared divided by N1 plus S2 squared divided by 14 as well.
That's something we want to do by hand tomorrow.
Now, what's the difference between these two? I can, if I copy it up here in the formula bar, I should get the same value, and then I change this minus to a plus. Okay, we'll interpret that in just a minute. Step number 5, the p-value. P-value only applies to hypothesis test, not the confidence interval. Okay, so with the chart, you know how to use that, Aaron? And with the computer?
So with the chart, it's not, you don't use it, but that's what, it's like eating to something.
So I'm going to look up the 1.43, right?
13.
It's negative. Does that matter?
No.
I'm going to ignore it for the chart, right? So negative 1.43. I'm on 13 degrees of freedom. Where does 1.43 fit in here?
Between 0.1 and 0.05.
Yep, it's right there. It's in between those two numbers. So my p-value with the chart is between 0.05 and 0.10. So with the chart, 0.05 less than p-value less than, whoops, 0.10. Okay. And with the computer, Christian, do you remember that command? You don't remember? Dalton remembers.
Equal T.
Chandler. Not norm. We're not using norm. We're using t-dist, right? T-dist dist. Which one? I'm doing the two-tailed this time. Now, by the way, what happens if I have a negative number? Is it going to work?
No.
No. So I'm going to put negative of that because I want it to be positive. Okay. With 13 degrees of freedom, and hopefully I get it in between 0.05 and 0.10. Okay. On your quiz tomorrow, you're going to use the chart. On your test next week, you're going to use the computer command, right?
Yeah.
So hopefully, drum roll please, is this going to be between 0.05 and 0.10?
If it's not, then we're screwed.
It's not. Why is it not? What did we forget on the chart?
What do we forget? Oh, 2.
You forgot to double it because it's a two-tailed test, right? So this is not really between 0.05 and 0.10. It's in between 0.10 and 0.20.
Go back to the chart.
Oh, you just have to double both of those.
Can we go back to the chart?
So this is the correct answer. And that's the correct answer. So because, remember, it's a two-tailed test, we forgot to double that.
Can you share this?
Yeah, sure.
Can we also get
Okay.
the other one shared?
Now, really quickly,
You said you're going to do on Thursday?
step 6 is reject or not. And the answer is alpha is right here.
Not reject.
Do not reject.
I forget what we're doing with rejected.
And step 7,
If the p-value is low, reject the null.
P-value is lower than the null hypothesis.
right. So the conclusion,
There is nothing.
there is not enough evidence of a difference between Earth and space rats. Okay, now can you see that with here? Let's talk a little bit about the confidence interval. Okay, remember when we're doing this, we're subtracting x1 bar and x2 bar. Okay, if they were the same, what would the difference be? It would be 0. Is 0 in my confidence interval? It is. So because 0 is in this interval, there is not a significant difference between Earth and the space rats. If, on the other hand, I'm just going to put a negative in here, hopefully. No, that didn't help. If that was negative 0.27, so these are both negative, would there be a significant difference?
Probably.
Yes, because 0 would not be in the interval. If they were both positive, would there be a significant difference?
Yes.
Yes, because 0 is not in the interval. Okay? Now, another way to think about the null hypothesis is if you subtract those, it would be 0, right? Okay? No, I went through that fast. We'll meet in here again tomorrow because they didn't think it'll be done with construction. So, quiz tomorrow is on chapter 21. Be sure you know the difference between dependent and independent. We will not do dependent samples. And oh, by the way, you need to use this on your final project.
So,
Okay.
and we're gonna have either or formulas, or we have the two formulas for tomorrow's quiz.
You should know how to do it both ways. I did it both ways. Did them simultaneously. Okay? All right. So I'll highlight that and
So for
I'm going to
the,
stop the recording.